Okay, so the next question that we got on the menu today is asking us what is the maximum angle that this ramp is going to be allowed to be inclined so that the box does not slide down the ramp. Okay, because if the box slides down the ramp, well, you know, they won't catch you slipping, and that's not great. So you don't want to be caught slipping. So what's the maximum angle that we can have? Let's actually draw our own diagram on this because I can't draw on the OneClass image. But let's get it started here. So we have a 50 kilogram mass like this. 50 kg. Okay, now we have no idea what this angle is. We want to find the maximum angle at which this will not be slipping down here. Okay, and the only thing that is preventing it from slipping is the frictional force. Okay, so let's actually draw all of our forces onto this system. I'll draw the forces in blue. So we have the frictional force, which is going to be going up the ramp. And we know that this is going to be equal to the coefficient of static friction, which is given as 0.235, multiplied by the normal force. Okay, so this is going to be our frictional force, and that's the only thing that's preventing it from sliding down. So less normal force means less frictional force. Okay, and another force that is definitely going to be here is the force of gravity, which is going to be straight down. So that's Fg. And that is equal to mg, which is equal to, what's the mass? The mass is 50 kilogram. Multiply that by 9.8 meters per second. And just to find that out quickly, so we have a numerical value, because the weight force is always going to be the same. It's never going to weigh less. No balloons attached to it, or nothing like that. Like, it's going to have a constant weight. So we got 50 times 9.8. We get 490. 490 newtons. Cool. Yeah, and the next force that we need is a normal force. Okay, our normal force will be like this. So this is Fn for F normal, and the normal force has to be perpendicular to the ramp. Okay, so this is perpendicular. Okay, awesome. So now another way that we can kind of handle this question to make things a lot easier is to have a tilted axis. Make that a different color so we can kind of have some connection on that. So tilted axes make math much easier. What I mean by tilted is you want to have them like this, so that they're pretty much in line with the ramp itself. Okay, now imagine this. Okay, so our F force is going to be perfectly in the x direction, in the negative x direction of these axes, and the Y force, which is the normal force, is going to be perfectly in the y direction. We only got one force that we need to make into our, we only have the gravitational force that we need to force to be changed. But if we had regular axes, like perfectly horizontal and perfectly vertical for x and y, we would need to adjust both the frictional force and the normal force, which is a little bit more difficult. So yeah, but to resolve the gravitational force to be in components that are perpendicular or parallel to the axes, we would just need something like this. So I'll put this in red. So you see these red arrows are perfectly in line or perfectly parallel and perpendicular to the axes. And we know that, if we draw them like this, we can show pretty clearly that those two vectors added together are going to be equal to the weight force. Okay, so let's call this FGY, and let's call this FGX. And if we have those, it will be a lot easier to deal with. And another thing that's important here is that the angle that they make here is going to be the same as the angle that is made over here with the ramp. Okay, so to prevent this from sliding, it's back to action here. So to prevent, angle, or nope, net force on tilted x-axis must be 0. Non-zero means slip in. Okay, so let's actually build an equation to kind of represent that. So we know that the sum of our x direction forces must be equal to 0. And we know that, well, if we have up the ramp as negative x, we're going to have negative FF plus FGX. Okay, so those two have to be equivalent to each other for this to be valid. Now we can rewrite these equations as we know that negative f of f. We can rewrite this as negative 0.235 Fn plus Fg times sine angle. Because you can see here from the diagram, from this little triangle section over here, for that triangle like associated with the gravitational force, if we want to get FGX, which is down the slope, you can kind of see with some trigonometric magic that it's going to have to be the angle, right? So yeah, but we have no idea what Fn is. We're going to need to do the sum of all forces in the y direction to solve for Fn, the normal force. Need all forces in y direction to get Fn. Oh, bless you. Thank you. Must be 0, or else block would sink into ramp or floats off of it. Which is certainly not something that we can really deal with. It's not sinking into the ramp, it's not floating off it, has to be 0. So Fy is got to be equal to 0. So let's look at our diagram for our y component forces. Positive is like flying off the ramp, so we only have n, the normal force, which is in the positive direction. So there we have positive Fn, and we have a negative force in the y direction, and it's Fgy. And you can see here it's going to be cos times Fg. So Fg cos angle. No idea what the angle is. We have to solve for that. Okay. So given that we have these two equations, we have a system of equations. We can solve for. Let's first solve for the normal force, and then we can keep it moving from there. So if we isolate Fn, Fn is equal to Fg cos theta, and Fg we know is 490 newtons, right? So 490 newtons multiplied by cos angle. Okay, so now that we have this relationship for Fn equals Fn, normal force, we can sub that into our previous equation for, so we'll sub this into our x forces equation. So here we have f of x is equal to 0, which was equal to it was negative 0.235 Fn. Add 490 newtons. That was the previous Fg. I'm just putting in the numerical value times cos. Was it cos up there? No, it was sine up there. My bad. Times sine theta. And of course, inside of here, we can sub in Fn into here. So we have 0 equals negative 2.35. Whoops, not 2.35, 0.235. 0.235. And we have to sub in this whole thing for Fn. So we got 490 newtons multiplied by cos theta, and plus 490 n, 490 newtons times sine theta. Okay, so let's bring that negative term to the other side of the equation, and let's actually multiply this in so we just have like single numbers. Okay, so 0.235 multiplied by 490 is 115.15. So we're going to have 115.15 newtons cos theta is equal to 490 newtons sine theta. And we're trying to solve for theta. Okay, so keep in mind that if we divide both sides by cos theta, and or what I'm trying to say here is that we know that tan theta is equal to sine theta over cos theta. Okay, so if we can get a cos theta in here, and then that's like cos theta or tan theta is equal to a number, and then we just do inverse tan, we can solve for theta. And that's my plan of attack here. So we're going to divide both sides by 490 and divide both sides by cos theta. So we're going to have 115.15 n divide by 490 newtons is equal to sine theta over cos theta, and that's equal to tan theta. And the numerical value of that calculation, 115.15, divide by 490, that's equal to 0.235. Hey, and that's exactly our coefficient of friction, which I'll get back to that. It's kind of some secret sauce here. Yeah, so given that we have this, we know that we can do theta is equal to arctan of 235. That's not cotangent, by the way. Arctan is a whole different operation. So we'll do arctan of 0.235, and the result of that is 13.2 degrees. So this is maximum angle before slipping. Okay, so 15 degrees, you know, that's pretty much flat with just like a little slope like this. Like It's not so steep that you would slide on it in the wintertime. But if you dropped a grape on there, it'd definitely be rolling. It's not super steep. But another key thing here is this is actually the definition of coefficient of friction. So, like this whole process we showed is like how this was originally derived, and like if you get a type of situation like this on the exam, you're probably going to need to show your derivation. But this is the definition of coefficient of friction. Of coefficient of static friction. Now it's important to specify the difference between static friction and kinetic friction or dynamic friction, but this is the definition of the coefficient of static friction. This is the tan of the angle when thing starts slipping down ramp. Okay, so this is actually where these coefficient of frictions even come from. Now you could just, like, if you wanted to, you could just say, okay, well, the maximum angle, we can just take the arctan of this, but the derivation is important. But sometimes you will need to calculate the coefficient of static friction yourself. Like, let's say you're trying to figure out a system like this, and let me see if I got any real life examples that I could show for this. So here I got a calendar. This can kind of represent a ramp, like this. So if I'm trying to figure out the coefficient of static friction of my calculator here, and I put it on like this, and of course I would want a better table, but if I had a protractor watching the angle I was raising it, the precise angle that this calculator just starts slipping, right there, okay, I'm not sure if you can see it properly, but it is slipping, so it'd be like the protractor measured whatever this angle is, take the tan of that would be the coefficient of friction for my calculator. Okay, so that'd be an example of like why you need this, why this be useful in real life, because most of the time you're not necessarily going to know the coefficient of friction, and it also depends on the surface. So my calculator on that calendar might have had a coefficient of friction of a certain value, but my calculator on top of a block of ice, completely different coefficient of friction, right? Ice is pretty slippery, so it's going to have a much lower coefficient of friction. So yeah, you will typically need to find this in many different ways, but it seems that the solution that we have here this is coming to the same conclusion, which is pretty cool. So okay, things are looking pretty good. They came to 13.2 degrees, so the above solution is good. Can be dangerous to use capital N as the normal force variable because it could be confused with the capital N for Newton force units. Fn, F subscript N is a more safe option. Okay, cool, awesome.